Reset method is used to make the math easier. Let me do an example of making the math easier. The reset method. Right now, I have a pen. So, it would be nice, you know, I remember sitting in on one instructor's Chem 4 lecture, and they said, you know, stoichiometry is just grams to moles, moles to grams. You know, but is that all there is to it? You know, when you do a stoichiometry calculation, there's always grams to moles, moles to grams. It would be nice if it was always that way, but there are lots of variations. And so do you want to memorize some kind of flow chart for each variation in that? That's, you know, that would take you a long time to develop, wouldn't it? There's lots of little variations in that, but I guess it could be done. Well, the same thing with this. You know, the reset method. I got to ask you a question. You know, why don't you just come up with some simple algorithmic way, you know, to use the reset? You know, you use the reset. But there's so many little variations. It makes it complicated. And so the best thing to do is just to do a bunch of them. And you will, actually. And so let's take a look at an example of reset method. So if I have the H2O plus the H2O liquid equilibrium like this, we call this equilibrium KW, right? KW for water ionization. We already know what it is at equilibrium. In pure water, what is it? Yeah, the 2 sig figs is 1.0 times 10 to the minus 7 molar hydronium. And this forms in a 1-to-1 ratio. It's going to be 1.0 times 10 to the minus 7 molar hydroxide. Now, what if I perturb that? How can I perturb this? Well, if I take some pure water and add some acid to it, that would perturb the equilibrium, right? And so let's say we're going to add some acid to this now. We have a system at equilibrium. We add some acid. All right, I'm going to add how much acid should I add? We could add carbonate, but carbonate's more complicated. I just want to add something that's going to either add hydronium or add hydroxide. Okay, hydrochloric acid, how much should we add? Maybe a little bit or a lot? Just a little bit. Let's how about we'll just add enough so that we add acid so that the concentration is equal to 0.100 molar. How about something like that? 0.100 molar. And so what that's going to do is it's going to perturb it, because now we are at equilibrium and then we add 0.100 molar acid. It screws things up. And so now we're at non-equilibrium conditions, which would be 0.100. And so I need 6 decimals. So 000 more, 1, 0 molar. 1, 2, 3, 4, 5, 6, 7. Yeah. And so I perturbed the hydronium, and then the hydroxides here, 1.0 times 10 to the minus 7 molar, like this. So now I have way too much product, right? Originally it was all balanced, and now I dumped in a whole bunch more hydronium. Which way is it going to shift? It's going to shift to the left or to the right? That pen's a little bit better. Switch color. It's got to shift to the left. I increase the product concentration. It's going to shift left. I don't have to calculate Q for that. And so the change is going to be minus X molar, minus X molar. No, I ignore water. I ignore water because It's liquid. And so I need to reestablish my equilibrium. My new equilibrium conditions are going to be point 1 with 5 zeros and a 1 0 molar. Oops, minus x molar. And a 1.0 times 10 to the minus 7 minus x molar. And so this is just equal to Kw. You know, Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. You should memorize this value. Do you have it memorized? What is it? 1.0 times 10 to the negative 14. And so this is going to equal 0.1 with 5 zeros. 510 minus x times 1.0 times 10 to the minus 7 minus x is equal to 1.0 times 10 to the negative 14. And then we just solve for x. All right, and so why don't you go ahead and solve for x now? And we'll come back here. Let me get some more things. I'll be right back. Tell me when somebody has the x value. This first person to get x, let me know. Okay. X equals 0.093. I'm sorry? All nines? 0.099. Okay, let's see. We're allowed 2 sig figs, so I guess we'll just carry like that. Is that what you? Yeah. What's the next digit after 9? 9. How many? So all 9s. Okay. All right, and so we go back over here and we'll calculate it. Okay. And so here, 0.100001 minus x is whatever. Go ahead and tell me what that is. Okay, well, how about this one? 1.0 times 10 to the minus 7 minus x is what? Actually, this is the first one I noticed. I noticed something weird about this one. What's weird about this one? 1.0 times, can you punch this out in your calculator? 1.0 times 10 to the minus 7 minus 0.09999. What's wrong with it? It comes out negative. Is that possible? It's impossible. So what's the other root that you got for x? 1 times 10 to the negative?
Wait, oh, actually, never mind.
Okay, so this can't be it here, because that's going to give us a negative molarity. We can't have that. And so the other x value is what?
9.9 times 10 to the -7.
Give me more digits. 9.9. Always at least one more digit.
I don't have any more. That's as far as I know.
Is it 0 after this?
I don't have any more digits after that.
Oh, you mean it's just, it's blank?
Yeah.
Okay, so it would be 0. So we'll go 9.90 times 10 to the -7. Okay, 9.90 times 10 to the -7 is impossible because 1 minus 9 is -8. Can't work. So that's wrong also. That's wrong. This is just a quadratic. It shouldn't be too difficult, right? Just a quadratic. We've had third order, fourth order, fifth order, which are more difficult. And so we shouldn't need any tricks to solve this. We should be able to just solve this just using straightforward math. Right? And so double check your calculation and then just give me the x value that you solved for. I'm going to set a time limit to this because I don't want to burn too much time doing just the quadratic. Just use your fancy calculator if you have one. Some of you have a fancy calculator, right? Let's use the fancy calculator. Or would you use successive approximations? Okay, 9.9 times 10 to the -8. Okay. 9.9 times 10 to the -8 would be 0.99. This is a 0 here. Times 10 to the -9, or 7, excuse me. Times 10 to the -7. Right? We'll make the so if we go 10 to the -8, yeah. And so this looks okay. How did you solve this one?
I graphed the left side equation and then the right side as two different functions on the other side.
Oh, okay. What are graphing calculators? So graphing calculators are allowed on the SAT? No? Yes? No? Yes? Okay. All right. Well, officially they aren't allowed in Chem, graphing calculators. So you'd have to think of some alternate way to solve this. No one's going to stop you from making a graph by hand. You can make a graph by hand. Nobody was going to stop you. So you could graph it if you want, but you'd have to do it manually instead of by a calculator. Someone let me know who doesn't have a graphing calculator what the x value is. Is it just the algebra? Is that it? The algebra causing you a little bit of a bog down here? Would you say yeah? Or the math is just kind of, You got the same answer as that? And how did you do it? Quadratic?
Yeah, there's a quadratic formula.
That has a quadratic formula? Okay, good. All right, and so how long did that take? What would you say how long that took? 5 minutes? About? For the first person to get it? 5 minutes or so? Maybe a little quicker the more of these you do. But anyway, let's try this here. And so why don't you go ahead and multiply this subtract this in your calculator. 0.1, then 5 zeros, 1, minus that. 9.9 times 10 to the minus 7, 8, or 0.99 times 10 to the minus 7. This one I can do in my head, I think. 0.99. This is going to be giving me 0.01. It was only two decimals, 0.99, and then the third was 0. Is that right?
Yeah.
Okay. And so this should be 0.01 times 10 to the minus 7 molar, which is going to be, we'll move the decimal 2 over 1, 2, and make this smaller. So this would be 1 times 10 to the minus 9 molar. And over here, what do we have? Actually, I have a calculator here. It's a lab calculator. This is TI-30XA. And so 0.1, 1, 2, 3, 4, 5 ones, 1 minus 9.9 times 10 to the minus 8. Oh, I think I mispunched it. Someone have it? 0.0. Well, let me redo it because I miskeyed it, I think. 0.1, 1, 2, 3, 4, 5 zeros and a 1 minus 9.9 times 10 to the minus 8. Oh, now I know. I didn't miskey it. The decimal's so small on TI, I can't even see it. 0.099. How many, it's like, I'll carry it a little bit farther. It doesn't matter. Eventually we're only going to be allowed 2, so let's go like this. Try to avoid round-off error here. Okay, and so what we need to do next is we need to double-check our K value. And so let's go ahead and double-check the K value next. And so to double check, I just multiply these two concentrations, the hydronium times the hydroxide. So I have the hydronium still in my calculator, so I'm not going to clear it. And then I'm just going to do times 1 times 10 to the negative 9. I should be able to do this in my head, but I'll just use the calculator. And I get 9, K value is 9.99 times 10 to the negative 11. 9.99 times 10 to the negative 11 is the same thing as, we round it. This would be the same thing as 0.999. Move the decimal place over here, make this smaller. We can make this bigger, times 10 to the minus 10. Does it look good? What's K supposed to be? Yeah, we're just off by 4 orders of magnitude. Is that good? Maybe round off error? No, probably calculation. So you need to go back and redo your calculations and double check them, right? And so why do the reset? Already on a simple problem like this, which is a simple problem to be honest, the math is already giving people trouble, right? And so we try to think of ways, because this simple problem, even though it's just a quadratic, is a pain. And so what are some of the simple ways we might have made our life a little bit easier? One of the nice things would be to do the simplifying summation. But can you do the simplifying summation here? Not really. This is big number here, so we might do a selective solution. It's possible if you want to get fancy and advanced. if you get fancy in advance, you say this is a swimming pool, but this is a cup of water. You know, so if you have a swimming pool and you lose a drop, insignificant, right? But if you just have a cup of water and you lose a drop, well, that could be significant. Or, you know, a milliliter of water and you lose a drop, that's significant. Because this is a tiny amount, that's a huge amount. So what we could do is we could do what's called a selective simplifying assumption. You know, if you feel comfortable with this, you could do that. You know, and that is, say x is much smaller than this, but x is not smaller than this. And then we have an x to solve for. If we do just the straightforward, flat-out simplifying assumption, x drops out from both sides. Why? Because, you know, the initial compared to the change we're assuming is small. Well, how can we fix that? Well, this is something called the reset. And one of the nice things about the reset is it resets one of the initials to 0. And so x compared, or 2x or 3x compared to 0 is always significant and does not drop out the equation. And then there's another reason for resetting, and the other reason for resetting is to make that simplifying assumption more probable. If you think about the change here, the change should be huge. Why is the change huge? Because this equilibrium should be all reactant, very little product. All of a sudden we dumped a huge amount over here, and so we expect a big change in the reverse, at least for this initial. For this initial, maybe not so big, but for this initial, huge change. Does that make sense? And so, you know, what was the trick we talked about? The trick we talked about is reset. Every semester, I have students who just struggle with the whole concept of resetting. And so it's not, you know, the thing is, it's not something that clicks right away because there's so many variations in how you use it and what, you know, scenarios you use it for. And so a lot of people think that they should be getting it. You know, I should understand it. I should understand how to apply it. But you can't really understand how to apply it because there's so many different applications for it. And so the best way to learn this is the shotgun approach. You look at a huge number of problems, right? And then you see that. Because if you just stare at one tree, okay, I know how to reset this one problem. You know, like when I was talking about the tree in the jungle, okay, I'm going to work at it. I know how to reset this. I figured it out. Do this step 1, step 2, step 3, right? But all you can do now is if you run across that same exact tree in the jungle, you're good. But how many different kinds of trees are there in the jungle? You know, so if somebody said to you, well, you know, I don't want to deal with that. Just give me some simple list of rules that I can identify each tree in the jungle. I'll know exactly what to do. Well, is that something that's simple? You just have a step 1, step 2, step 3? No, I mean, that's something that you have to study a lot of trees in order to identify, right? And so the problem is that people have an idea that it's supposed to come easy, that this whole reset. I mean, if you just look at one type of problem, it should come easy because it's the same thing. But in the general scheme of things, and I don't want to discourage you, all it takes is some practice, and you'll get plenty of practice because in chapter 16, we pretty much use it the same way. And what is that way? Well, here, let's set this up for reset. So here's my new initial condition, and I think, should I reset this to the right or should I reset it to the left? You look at that k value, and you should reset it to the left. And so when we reset it to left, what is the limiting reagent, the LR here? Hydroxide's the limiting reagent, so I'm going to reset this. And so it's going to be minus Y molar minus Y molar. Here. Where we know that Y must be equal to the limiting reagent. And so I'm going to get my reset initial conditions, or my new initial conditions. This is going to be 0 molar. And over here I'm going to get, well, I actually overdid it with the sig figs. I'm only allowed 3 decimal places here. And so I'm going to get 0.100 molar. So we get 0 molar and 0.100 molar. Okay, now let's do the math. Okay, here the change is going to be to the right or to the left? To the right, because there's 0 here. And so this is going to be plus X molar, plus X molar. And so at equilibrium, I'm going to have 0.100 plus X molar, and over here I'm going to have X molar. And so Kw is going to equal 0.100 plus X times X. This is equal to 1.0 times 10 to the negative 14. All right, now how long do you think it'll take you to solve for X? Well, this is pretty easy to get in the quadratic form. X squared plus 0.100 X minus 1.0 times 10 to the negative 14 is equal to 0. Okay, punch that into your fancy calculator, and what do you get for your X? Give me one more digit. Always give me one more digit than 9.50 times 10 to the negative 14. Okay. So, how long did that take you? A couple of minutes, right? Versus the other problem. The other problem, we didn't even get an answer. I already waited like more than 5 minutes. And so the question I have is, why don't you want to reset? I mean, it just doesn't make sense not to try to learn it. A lot of people give up. They don't want to learn it because it's not presented in the book in a formal manner.
Can I just ask, how did you get the 0.100 molar? Is there like something you have to minus?
Yeah, I minused 1.0. Take 0.1 0.001 minus 1.0 times 10 to the minus 7, you get 0.100. In other words, the 0.100 here came from the HCl. This is the perturbation by adding HCl. The HCl just added another 0.100 molar worth of hydronium. Originally I had 1 times 10 to the minus 7. That's 1 times 10 to the minus 7 there. So that's fine. I told you that Petrucci does the reset, right? They just skip all the steps. That's it. I'll show you how they would have done this problem. But the other thing is, I could have done this problem even faster. What if you use a simplifying assumption? Or if we use the simplifying assumption, then KW is equal to 0.100 plus X times X. And so if we apply the simplifying assumption, we'd say that 0.100 plus X is about equal to 0.100. Adding one drop to this is not going to do anything. And then solve for X. If we solve for X, then X comes out to 1. What does X come out to? 1.0 times 10 to the negative 14 divided by 10 to the negative 1, so 10 to the negative 13. Negative 13, is that right?
I got that for the first one we did too.
You got 1.0 times 10 to the negative 13 for using the quadratic on the Casio. Did anybody else get this value here? You got 9.9 times 10 to the negative 13. We get a lot of variation. Times 10 to the negative 14. which if you got 9.9, then yours is closer to mine. Mine is 10. This is 10 times 10 to the negative 14. And so 9.9 is a heck of a lot closer than, than 9.5. Anybody else? This is a good time to check your calculators and your calculations before, the test to make sure. That you can do the quadratic and the other calculations. Well, let's try both of them. All right, it's easy to check, right? It's easy to check because we just K. And so the first one, 9.5 times 10 to the minus 14. That means this is going to be 9.50 times 10 to the minus 14 molar. And then over here, this is 0.100 plus that. And so 0.100 plus that is going to be 0.100. So I need how many digits? I need 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 9, 5. This is too many sig figs here, but we'll carry it. Do you see how much of a negligible addition that was? But anyway, we'll go ahead and punch in our calculator to avoid round off error. So it's going to be 0.1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 zeros. Can you punch that in your calculator? 0.1 with 12 zeros and then a 9.5. Will that enter into your calculator? Yeah?
It comes off as 0.1.
It comes off, your calculator won't take it. We'll just round it. That's all right. We'll just go ahead and round it. So we round it, and then we calculate our K value from here. And so it's going to be 0.1 times that, which is going to give us 0.95 times 10 to the minus 14. What should K be? K should be 1 times 10 to the minus 14. So I think, am I off because of rounding error? I'm about 5% off. Am I 5% off because of rounding error or calculation error? Do you think? What do you think? Rounding error? This is why I asked you what the other digits were. You just said a 0, right? It's all zeros. So it's not a rounding error. This must be a calculation error. So we should go back and double check the calculation. Now, if we use this number here, okay, let's use that number to calculate it via the simplifying assumption. If we use that number that we got from the simplifying assumption, then we're going to have, this is going to be 1.0 times 10 to the negative 13, and this is going to be 0.10, okay, I need 12, wait, no, this 10 times, oh no, 1.0. So I need 12 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Your calculator is not going to take this, right? And it's just going to round it to 0.1. So you might as well just do 0.1 times 1 times 10 to the negative 13. And that gives us 1.0 times 10 to the negative 14. It's supposed to be 1.0 times 10 to the negative 14. So there must have been a mistake because the quadratic should have given us a more accurate answer. The simplifying assumption makes, a guess, but in this case, was the simplifying assumption justified? Yeah, I didn't even check the justification here because it's 10 to the negative 13 over 10 to the negative 1 times 10 squared, which gives us what percentage? So this is going to be 10 to the negative 11, 10 to the negative 10. 10 to the negative 10% is way less than 5%. And so, just by sight, it's a tiny change compared to our initial, right? You can see that. And so when you have a percent change like this, then there's no difference. If we use the quadratic, we just wasted time because the simplifying assumption would have given us an equally good answer. Because the digits that would be different don't even register in your calculator. I mean, these digits would be different way out here, right? Slightly different, not much. Actually, in this case, If you do the quadratic and you do the simplifying assumption, you get the same answer. I've done it. I just don't have my calculator, and I didn't put on the projector, but the quadratic and the simplifying assumption give you the same answer. Now, how quick is that? If we use the simplifying assumption to solve it, less than a minute, we have our x value. And so somebody who doesn't reset is there, 5 minutes. I don't know. By now, do you think they would have gotten the x? Versus somebody who just reset it, knew what they're doing? That's a huge time difference, isn't that? So don't get discouraged. Let me show you what the book does, and this is the way we're going to do it too. What we did was this. We had a system at equilibrium. We perturbed it by adding some hydronium from HCl. And then we got new initial conditions, and then we reset the new initial conditions, right? Get it? In this chapter, we're going to do it a little bit differently. We're never going to start off at equilibrium. We don't start here at equilibrium. In this chapter, all we're dealing with is acids and bases. And we want to see, how our acids and bases are going to impact the pH. What we're interested in is the pH, the total hydronium. And so what we do here is this. And this is what your book does, and they're going to skip even more steps in doing this. But what we're going to assume is the initial from water is going to be 0 molar and 0 molar. So what we assume is we're just going to reset that equilibrium. It was 10 to the minus 7 molar, 10 to the minus 7 molar. We just reset it to 0 and 0. Right? And then we do the initial from the HCl. The initial from the HCl is going to be 0.100 molar hydronium from the HCl and no hydroxide from the HCl. And then we get the total initial. The total initial will be the initial from water, which is 0 because we just reset it. Automatically we reset it. Do you remember doing that yesterday, right? We just reset it. And the way the resetting is like, it's kind of ridiculous because if you have a container of water, can you stop the molecules from colliding? You say you stay there, don't collide, right? There's no barrier; they're going to be colliding. And so this is just a mental thing to make the calculation easier. And so we do 0 and 0 with 0.100, and so we start off with 0.100 molar and 0 molar. Okay, so we start off with the initial from the acid in here. Do you see how that saved us some work? Because we didn't have to do the equilibrium and then perturb the equilibrium and then get the new initial and then reset that new initial. We just start off with 0 from water and then just add the hydronium from HCl, and then we start here and then say, okay, now the waters, you can collide. And now the waters can collide, they're going to collide. They're going to do plus x molar and plus x molar. But here, is this plus x molar going to be 10 to the minus 7? Is the x going to be plus, because I know autoionization of water produces 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide. So do I already know what x is? It's going to be 10 to the minus 7 and 10 to the minus 7.
No, because you've got hydronium for
Yeah, right. It cannot be. X is going to be much smaller than 10 to the minus 7 molar. Why? There are two reasons why. One, because of this Le Chatelier's type effect. If we already have a whole bunch of product to begin with, we don't need to generate that much extra. That's one. Two, it's just chemical reactivity. Think about this. If you have a huge amount of predator and a tiny amount of prey, as soon as a little bit of hydroxide is produced, what's going to happen? Hydronium attacks, and there's lots and lots of predator here. And so if there was no predator here, then, if this was 0 and 0, there's no predator, then you can generate the maximum amount. What is that maximum amount? It's 10 to the minus 7 molar and 10 to the minus 7 molar. But now, if you have a huge amount of hydronium, which is the acid, and the acid wants to attack the base, then that's going to keep the population down. And that means that these values are going to be way smaller. In fact, how small? Well, we just calculated. It's going to be 1 times 10 to the minus 13, was it? Yeah, 1 times 10 to the minus 13. Normally, it's 1 times 10 to the minus 7. The hydroxide normally goes to 10 to the minus 7 molar, but the population is way down to 10 to the minus 13 molar because so much hydronium is there to begin with. It will attack it as soon as it's formed, and it can never reach that. And so we get the same answer here because this is the exact same setup. But we skipped a step, And this is the way we're going to do all of them, and this is the way Petrucci does all of them. He just doesn't use that jargon I use, that whole reset jargon is what I do. Okay? And fortunately, all the problems are the same in this chapter, so you don't have to worry about too many variations, unlike chapter 15. All right, that was quite a long answer to that question. Are there other questions? I missed the office. No other questions? All right, let's talk about the lab today. What's the next ion we're going to analyze for? Oh, yeah, I made a mistake in my syllabus. I thought it was posted, but we do have class on Monday. I know some people have made plans already for a holiday Monday, but I'm going to record it, so. And then I don't take attendance during lecture days, only lab days. You don't have to worry about missing it, adversely affecting. You can just watch the recording. We have school on Monday. Sorry. On the syllabus I put Washington's Day holiday because I just used last semester's syllabus. And it was Washington's Day. But, No. The only time we're going to have off is Thanksgiving, Thursday and Friday. This Thursday. Not much holiday in the fall. And no spring break. No President's Day. No Columbus Day. We aren't off on Columbus Day either. All right, what ion are we testing for next? After iron comes aluminum or chromium? Aluminum? Actually, I heard mixed answers. Was it aluminum or chromium? Aluminum's correct? All right. For the aluminum analysis, we start from the beginning. If our original unknown, this will be observational, if our original unknown aqueous contains aluminum, then when we add the HCl, what should happen? In the very first step of the analysis, what happens when we add the HCl to aluminum ions?
It becomes, well, the aluminum ions were originally aluminum hydroxide, and then we add the...
No, I'm all the way back at the beginning. All the way back to the beginning. Aluminum doesn't become silver chloride. The silver ions react with HCl. What about the aluminum ions? Do they react with the HCl? No, and it's important, otherwise we can't separate silver. So we need to know that aluminum does not react with HCl. Al3 plus does not react with chloride. Otherwise we'll have trouble at the silver step and we have to compensate for that. Okay, then what did we do to the decantate after this? We added the solution 1 plus the, what was it, the ammonium, what did I call this? Ammonium buffer. We added this and then we get a very low density white precipitate. It's almost transparent, so hard to see. And it doesn't really settle on the bottom. You know, it's like a cloud, wispy cloud in solution. Well, anyway, that's aluminum plus 3 ammonia plus 3 H2O liquid gives us aluminum hydroxide solid plus 3 ammonium chlorides. Oh, no, not chlorides, sorry. 3 ammoniums, this is net ionic. This will be the net ionic equation here. The driving force for this is, yeah, precipitation. And what kind of reaction is this? Metathesis. Why am I adding ammonium? Why, ammonium is a product. If I add ammonium, Le Chatelier says shift to the left. Tell me why I'm adding the ammonium.
Is it possible enough reaction can take place if there's too much ammonia?
If there's too much ammonia, another reaction can take place. What is that reaction? Yeah, magnesium hydroxide and others could form potentially. Okay, after we added the ammonium, what came next? The hydrogen peroxide or the hydroxide? Or both at the same time? Well, let's do it in sequence. Yeah, then you should prep your notebook a little bit like so it's a little easier to follow. You know, the sequence of steps. When you get your actual unknown, you don't have every ion in there. If you don't have every ion in there, what happens is you have to eliminate branches. You have to eliminate that entire branch. But if you're just going through it step by step, paragraph by paragraph, sentence by sentence, you're not going to know what to do, really. You don't know you've got to jump from here to there, unless you can visually see it. So it'll make your life easier. Try to look at the flow chart. There's one other thing about the unknown. When you do, during your known, you can ask me questions, but when you do your unknown, you can't ask anybody for help, including me. I'll tell you, so many students come up to me and ask me, what should I do now? I didn't get any precipitate. What do I do next? I'm supposed to centrifuge it. I centrifuge it, but nothing happened because there's no precipitate. What do I do? I don't help them. They're on their own. If they have the flow chart, it's easy to see what to do. So make sure you have your flow chart there too. And then refer to it so you know kind of what you're doing. And so what comes next? The hydroxide or the hydrogen peroxide? This is why we rewrite things into our procedure, making them a lot simpler than they are in the the procedure in the lab manual. Because the procedure in the lab manual is hard to pinpoint where you are and hard to pinpoint what you're doing. Or maybe I'm wrong. I'm just doing this from memory. Maybe what comes after the ammonium steps?
HCl.
Hmm?
More HCl.
More HCl.
Yeah.
Okay.
And aluminum reagent.
And then what?
But it says 6 more HCl and aluminum reagent.
Oh no. Unfortunately, you're in the wrong place. Wrong place. If you did aluminum here, you'd be in trouble because you would get the iron and you would get the chromium screwing things up.
It says to add HCl in order to get the aluminum ion in an aqueous state.
Okay.
And then from there, we have to separate out barium and chromate by having barium to get a precipitate, and then we react with.
Well, before, how do you get the chromate? Because right now we just have chromium 3, not chromate. At this point, we should only have chromium 3. So how did you get the chromate? You have to heat it, and you have to add some other stuff to make. How do you make chromate? Look. Can you look at the flow chart and say, just see how you made the chromate? There's one box that should be chromate, and above that should be another box that contains something else. Chromium 3, or chromium 3 hydroxide, or something. I suspect it's chromium 3 hydroxide. And then you add what to it?
Sodium hydroxide and hydrogen peroxide.
Sodium hydroxide and hydrogen peroxide. So we're adding sodium hydroxide next. So just the question was, what do we add next? Sodium hydroxide or peroxide? It sounds like we add sodium hydroxide. So sodium hydroxide, we take the PPT from 2 and add sodium hydroxide to this. And what happens to the precipitate, if anything?
It should dissolve. The precipitate should dissolve.
The precipitate dissolves? And so the equation for this is aluminum hydroxide solid plus an extra hydroxide. The extra hydroxide will act as a ligand. Now we've separated out now we're adding the hydroxide, but we've separated out the magnesium and the other group 2 and group 1 cations. And so in this case, the hydroxide will attack the aluminum to form the complex. What's this complex called? Tetrahydroxoaluminate. Okay, then what do we do? Do we separate or do we add the hydrogen peroxide? We add the hydrogen peroxide. So the solution in 3 plus the hydrogen peroxide, what does the hydrogen peroxide do to the aluminum? Nothing. It's already oxidized. So NR, we should get no reaction. That is the tetrahydroxoaluminate plus the hydrogen peroxide. Aluminum plus 4, we don't, and hydrogen peroxide does not oxidize water. In fact, hydrogen peroxide does. Well, at these concentrations. All right, next. After we add the hydrogen peroxide, then what do we do?
Then if the liquid is kind of, after we remove some, are we talking about the chromium and the aluminum?
No, I mean the aluminum. What do we do to the solution here? I mean, it could react with the. Do we add barium next? What do we add?
We're not done with the aluminum.
Okay. What do we add to the aluminum next?
We added hydrochloric acid.
Hydrochloric acid? So, okay. So we add hydrochloric acid. So, plus hydrochloric acid, this is, you know, will you see a visible reaction? No, but with hydrochloric acid, what the hydrochloric acid is going to do is it's going to react with all the hydroxide ligands here. And so we'll have 4 H pluses, and then we'll be left with the aqua complex of aluminum, just Al3 plus 4 water. And so the acid can actually attack the hydroxyl ligand and convert the hydroxide into water. Okay, then what?
Now we separate out the aluminum by using ammonia to form aluminum hydroxide precipitate.
Okay. So here we go to solution 5 and then add ammonia. Do we have to add the buffer or just straight ammonia? Straight ammonia. And then we should get a white PPT. We don't have to worry about the buffer because there shouldn't be a bunch of other stuff, plus 2 cations in there. We should have gotten rid of those. So this is going to be Al3 plus 3 ammonias plus 3 waters yields aluminum hydroxide. Solid plus 3 ammonium. What you guys should do is you should always double check your equations to make sure that they're balanced. You know, a lot of people could have saw that their equation was wrong just by seeing if it was balanced or not balanced. A lot of these you could see if it's balanced or not balanced just by sight. It's not that tricky in that sense. All right, next, what did we do?
We redissolve it
Redissolve it?
with hydrochloric acid.
Okay. So we redissolve this with hydrochloric acid. So we'll take the 7. We'll take the precipitate from 6 plus hydrochloric acid, and this should redissolve it to form a CCS, precipitate dissolved. And so the equation for that is just aluminum hydroxide solid plus 3 H plus should give us Al3 plus 3 waters. And then what?
You add ammonia with aluminum.
Okay. So we add ammonia or ammonium.
Ammonia.
Okay. So we'll take the solution from 7 plus ammonia plus aluminon. Now aluminon, what is that? Aluminon is like a dye that's going to color or precipitate. And so we don't need a whole bunch of dye. It's kind of concentrated and gives a pretty good color. And we form, you know, normally what color is aluminum hydroxide?
Colorless white.
Yeah, white colorless. But if we have some dye in there, do you know what color this is?
Red.
Red. And so we put a double dagger here to indicate it's not pure. And what we do is we centrifuge this. When you centrifuge it, this is what it looks like. You have what's called like a red gelatinous solid layer, like a jello layer, and it's a solid. Looks like a semi-solid, but it's a solid. It's not a liquid. And so we have what's called the red lake. It looks like a red lake because the water above here looks like the sky. And so this solution looks like the sky above the red lake. And the precipitate looks like the red lake. And so you have this little miniature lake in the test tube, which is, and so this is the red lake test for this. And so what's the equation for this? Aluminum is an organic dye, so it's just going to be Al3 plus 3 ammonia plus 3H2O liquid yields aluminon. I mean, doesn't yield. We put aluminon over the arrow because it's not really a reactant, it's just a coloring agent. We just need a little bit to contaminate our crystals to get a PPT. If we get a red solution, it's a negative. A red solution is negative. The red PPT is positive. Okay. Well, I've already spent enough time talking, I think, today. We'll look at the other ions next time. So just keep cookbooking the procedure, but as you're cookbooking the procedure, try to refer back to the flow chart to see, where you are in the overall scheme of the analysis. Okay.